So what I want to do today is I first want to talk about requirements for this week and next week. And then I'm actually going to do some review problems to start class today because we haven't had class. It's been 2 weeks, right? It's been 2 weeks since we've all come together.
Yeah, I think so.
Yes, 2 weeks.
Wow, feels like forever, doesn't it?
Yeah.
Yeah, it does.
All right. So everybody could see my, I got the classroom loaded up for us. Everybody can see it okay?
Yep.
Yes.
All right, so if you look at our course outline, I'm going to change it up just a little bit. Today we were going to learn about confidence intervals for a mean, but I'm actually going to move that to next week. So if you notice, the college is actually closed next Tuesday before election day. Did everyone know that?
Did not.
Yes.
Yeah.
Some people did, some people didn't.
Okay.
So the college, so all classes, it's not just me, all classes are canceled. So I hope everyone goes out and votes. Have people filled out their ballot, gonna mail it in? I'm just curious.
I'm actually going to the polls.
You gonna go?
I'm early voting tomorrow.
Good luck. One of my friends did early voting the other day and he said he had to wait 5 hours for it. So good luck.
Yeah, I tried yesterday. The line was way too long, so I'm gonna go tomorrow.
Yeah. So
I'm hoping it eases up by Wednesday a little bit. I mean, I guess I'm not hoping it eases up, but I'm hoping it doesn't take too long.
Sure.
Yeah.
Sure. So yeah, I actually dropped my ballot off yesterday in a secure drop box. So all right, Bill, because there's no class, so today I'm actually not going to cover confidence intervals for a mean. You're going to do that on your own next week. I'll explain that. So if you look into the classroom here, down in the two corners, I have the tab for today's class open and the tab for next week open. So under the week 9 tab, under the post-class requirements, I just have more lectures basically reviewing exactly what I'm going to talk about today. Okay, so if you at the end of class today, if you're like, this didn't make too much sense, there's 2 different lectures here that walk you through examples. Your homework this week, it's 6 questions, I believe. Yeah, so it's short, but if you pay attention to lecture today, you'll be able to knock these out of the park. I promise you. Okay. And then next week next week under week 10. So we're actually not meeting in class, okay, because class is canceled for election day. So what you're going to have to do is you're going to have to learn this topic of the T distribution and confidence intervals on your own, okay, without my help. I have 3 different lectures here for you guys. I think my lectures total maybe an hour and a half. So you'll just have to watch these all on your own and then take your week 10 quiz. Okay. So because of, normally I have the quizzes be 2 attempts, but because this one, there's no in-class person, this one actually has unlimited attempts. Okay. Does everybody kind of understand those requirements? So you'll be responsible for next week's lectures just without me in class.
Yep.
Yep.
All right. I get good vibes. I think everyone will do great. So this week 10 assignment, or week 9 assignment, excuse me, is due Monday the 2nd. And then the week 10 assignment is due Monday the 9th. Okay, so I'll send out reminder emails for you over the next 2 weeks, okay? All right. Any questions before I move on? All right, so no questions. Just remember to vote. Doesn't matter who you vote for, just make sure you go vote. Who we kidding? It does matter who you vote for. All right. Yes, it sure does. So have handy your graphing calculators today, either your TI-83 or your TI-84 today, okay? I'm gonna flip flop between them. but we're going to use them extensively in class today. All right, extensively. Okay. So I actually want to start today's class with a review from literally 3 weeks ago. Okay, because you're going to get one question on your quiz this week like this. Okay. So according to the Department of Health, all right, statistics students sleep an average of 8 hours a night. Okay. So right there, what they're telling you is they're telling you the mean, which is that Greek letter mu is 8 hours. Does that sound about right? You guys you think 8 hours of sleep?
Not really for me.
I'll be
On a good night.
Must be nice. I just made this up anyway, so don't think this is real. Okay. Next part says, assume that the hours of sleep here, all right, that statistics students get per night, all right, follows a normal distribution, and then I also tell you the standard deviation. Oops, sorry. Is 1.5 hours. Okay. All right, so I got 3 quick questions, and we're just going to burn through these really quickly. If a statistics student is selected at random, okay, what is the probability they sleep less than 6 hours a night? So I'm going to start by defining this variable, right? I'm going to let the random variable x be equal to the amount of sleep by a randomly selected stat student. And I want to find the probability that this x is less than 6, okay? Just out of curiosity, before I continue with this, does this kind of ring a bell to what we were doing a couple weeks ago?
Yes.
Yes. Now we have to draw a little graph.
Yes, thank you very much. I appreciate that. Yeah, I think the drawing helps, right? So we know that x here, the hours of sleep students get per night, follows a normal distribution. So you're going to draw this bell curve. It's going to be centered at 8. And I want to be less than 6. Okay. All right. So to answer all the probability questions today, all right, we're going to use our graphing calculator. Okay. Does anybody remember what the option was to use the graphing calculator? What it was called?
Binom CDF.
You're
or
close.
PDF?
It's not the Binom CDF. So let me load up I'll do the first one in the TI-83.
The normal.
A normal CDF?
Oh, right, the normal.
Yep. So we're going to go second function, distribution, DISTR. And you're always, whenever we're going to, and I'll give you a hint, okay? Every problem this week and on your quiz online this week is the normal CDF. So it's going to be normal CDF. Okay. So I'm going to go back here for a second. So in the normal CDF, you have to put in 4 things. Okay. You have to put in a lower value, comma, an upper value, the mean, comma, and then the standard deviation. Okay. So when this is a left-tailed like this, okay, does anybody remember what we have to put for the lower?
Negative 9,999.
Yep, negative 99999, something ridiculous. And then the upper, we're going to go to 6, wherever my graph tells me to stop. And then we're going to put in the mean over here, 8 hours, and the standard deviation, 1.5. So going back to this, it's negative 9999, comma 6, comma 8, comma 1.5, close the parentheses. And if you were doing this following along with me at home, how many people got this number right here?
Yep.
Yep.
Okay, so it's 0.0912. Piece of cake? Does the calculator make everything easier?
Much easier.
Yes.
I think so. All right, so let's do another one here. Okay, so if a statistics student is selected at random, what's the probability to sleep more than 8.5 hours? So it's probably X is greater than 8.5. It's a really bad curve today. And I want to be greater, so I'm going to shade to the right. So again, we're going to use our normal CDF. All right, in this case, what's my lower value here?
8.5.
Yep, and then my upper is going to be,
9999.
yep, 9999. And then just the mean and the standard deviation, piece of cake. I'll do the TI-84 here. So 8.5, 9999, 8, 1.5. And then if you had the TI-83, you just had to put this in. And this one is 0.3694. All right. All right, let's do the last one. If a statistics student is selected at random, what is the probability they sleep between 5 and 9 hours a night? All right, so again, this is going to be normal CDF. Okay, but when I draw this, centered at 8, I want to be between 5 and 9. So when you have this between stuff like this, all right, what's my lower value for this example?
5,
5.
And my upper?
9.
Yep, perfect. And then mean is 8, standard deviation is 1.5. So normal CDF, 5, 9, 8, 1.5. So if you have to plug it in the TI-83, you plug it in like this. And you get 0.7248 when I round it. Anybody else get that?
Looks right.
Yes.
All right. So you're going to have, so as I said, you have 6 questions on your quiz this week, and your first question is going to be exactly like this. So everyone think they could do great on it?
Oh, yeah.
Yep.
Okay. So now that I'm thinking about it, we did these type of problems 3 weeks ago. Holy cow. So does anybody need me to slow down, or can I go to the next slide?
When we're putting in our answers, are we rounding to the 4th place?
Yes. Yes. The reason I do it to the 4th place is because when we would do it by hand, or when we would do it with the table goes to 4 decimal places. So I just would do it to 4 decimal places here. It's just by habit. Make sense?
Yep. Thanks.
Everybody okay?
Yeah.
All right. Let's move on to another type of example. Okay. And this is more related to what we did 2 weeks ago. Okay. All right. So according to the Department of Education, college students spend an average of 150 minutes. So that's mu is 150 minutes per day on their phones with a standard deviation of 75 minutes. Okay. What do you guys think? Does that sound about right?
I don't even
Yes.
know.
Yeah, it's actually kind of embarrassing, right? Like my phone gives me my, status update, like how many minutes you spent on your phone today. And I'm always really embarrassed by the number. Um, we're all kind of addicted to it. But notice how what it doesn't say here is like, it doesn't say, that the time that college students spend on their phone is normally distributed. It doesn't say that at all. That's missing from this problem, okay? The next thing it says is suppose a random sample of 36 college students is taken and the mean time is recorded. Okay? So I'm going to define this variable, okay? I'm going to let x bar be equal to the mean time spent on phone in a sample of 36 students, okay? All right, this is a continuous random variable. All right, because like before I talk to the 36 students, like I don't know what the average is going to be. So now here's the thing. Does anybody remember what I said was the most important theorem of the class?
Central limit theorem.
Say it louder.
Central limit theorem.
The central limit theorem, absolutely, okay. All right, if you recall what the central limit theorem says, since the sample size does anybody remember what I said the sample size had to be greater than for
30.
Yep, since the sample size is greater than 30, the sampling distribution of this variable of x bar will be normally distributed with. Okay, so when something's normally distributed, you got to say it's mean, which we denote as mu sub x bar. All right, so it's the average of the averages. Does anybody remember what I said that was, what that would be equal to?
It's the same as X bar.
Close, not x bar, but it's the same as,
Mu.
yeah, this right here. So on average, the average of the averages should be the average, okay? And then the standard deviation was something we called the standard error. It's equal to, we denote it as sigma sub x bar. And does anybody remember the formula for that?
I think it's sigma over the square root of n.
You know what? That's perfect. So I'm going to take 75 and divide it by the square root of 36. I'm going to grab my trusty calculator for this. So it's really 75 divided by 6, but, and we get 12.5. So whenever you see these problems, when I say, something like the mean and a sample size of 36, okay, like this is going to be questions 2 and 3 on your quiz this week. Just remember, this is the most important step. Okay, just take the standard deviation, divide it by the square root of n, and use this value now in your calculator. Okay. So watch, you're going to get a question just like this, okay? What is the probability that the sample mean, this x bar, is less than 140 minutes a day? So it's probably that x bar is less than 140. Well, how is x bar distributed? Well, we know it's normally distributed. It should be centered at 150. And I want to be less than 140. Right, so what option in my calculator will I use for this?
Normal CDF.
Normal CDF. Remember how I said that? Like every problem today, okay? Like I'm going to be a broken record a little bit later on. Like I'm going to say, oh, what do I use? every problem today is a normal CDF. Okay, so it's normal CDF. So my lower value, because it's a left-tailed test, is negative 9999, or left-tailed probability, sorry. My upper, I'm going up to 140. The mean I got right here is 150. And the standard deviation is this value here. So always use for these problems, sigma x bar, okay? Trusty calculator here. So second function, normal CDF. My lower here is negative 9999, 140. The mean is 150. And then I use that standard error, which was 12.5. And you should get this, which is 0.2119 when I round it. Not too bad?
That's
Nope.
pretty good.
Okay. You guys, I'm just curious, do you notice that you don't even need the drawing anymore the more of these you do, or do you still like the drawing?
I
Uh,
personally
in my
still like
head.
the drawing. Only because the 1- ones always sort of get me.
I hear you. Yeah, I like the drawings too. It just helps me keeps me on track. But like the more you do, the less you need the drawings. Like I'll even show you this one.
If I'm trying to be like speedy, I just never draw it.
Yeah.
I also check that like the number makes sense that I get at the end. So if it's like if it's like a small tail that I'm looking at and I'm getting like a big number, then I know that I'm wrong.
That's great. That's awesome. So for this one here, this next one, what is the probability the sample mean is between 140 and 160? Well, because I'm telling you it's between, right? Like you just know that it's a normal CDF between the lower value 140, the upper value 160, and then just still put in the mean of 150 and the standard deviation of 12.5. So second function distribution, normal CDF, 140, comma, 160, comma, 150, comma, 12.5. You get 0.5763. Anybody else get that one?
I did.
Yep.
Yeah.
5763. Okay, boom. All right, so this is questions. So we've done questions now, like question 1 on your quiz, question 2 and 3. And you'll also get a question just like this on the final exam, okay, which is gonna come a lot quicker than we think. But like, hopefully this, with your calculator, it's not too bad. All right, everybody feel good review?
Yeah.
I just have a question.
Sure.
There's not going to be a question where it's the sample is less than 30, right?
So it can, yes. So actually, good question. Let me show you something on your quiz. So on your quiz, it is actually, so that's a fantastic question. Okay, like notice here how it's, can you guys see on here?
Yeah.
How it says, what is the probability of random sample of 10 batteries? Like if I tell you if it's less than 30, the problem has to say it's normally distributed. So if the original variable is normally distributed, sample size doesn't need to be over 30, okay? But if like in this problem here, I didn't say it was normally distributed, so the sample size needed to be over 30. Does that help answer your question?
Yes, thank you.
Good question. Okay. All right. Now let's go on to the new stuff, okay? So now we want to talk about the sampling distribution of the sample proportion, okay? So this next part is covered in your post-class assignment. This is going to be questions numbers 4 through 6, so numbers 4, 5, and 6. And you're also going to question exactly like this on the final exam, okay? So this is a new statistic that we're going to be talking about. And it's this statistic called a sample proportion. All right. And you've all seen this sample proportion before, especially in the news. You know, like we have a big election coming up next Tuesday, right? We kind of talked about that a little bit, but like, you know, every day it seems like there's a new poll that comes out and they say something like 40% of Americans believe this, or 60% of Americans believe this, whatever. That's just this sample proportion. Let me give you the formal definition of this, okay? All right, suppose that a random sample of size n, so I'm giving you the sample size, okay, is obtained from a population in which each individual either does or does not have a certain characteristic. So only 2 characteristics. Okay, so that we wouldn't use this sample proportion for like different eye colors, like brown, green, blue, whatever. So this is like, are you gonna vote Republican or Democrat, okay? Please don't vote third party. No, you can vote third party. Don't, I didn't say that, but like only 2 characteristics. You're gonna vote the Dems or the Republicans, okay? You're gonna vote for Dems or not vote for Dems. I guess you guys can see who I'm voting for. Okay. So the sample proportion we denote by this symbol here. Okay, it got cut off a little bit. It's P with a little, looks like a little caret sign on top of it. Okay, this is read as P hat. Okay, right. I actually love that, right? Like, statisticians really have a great naming convention, right? Like going back, oh, let's just call this X bar because it looks like an X with a bar over it. Let's just call this P hat because it looks like a P with a hat over it. Okay. Nobody else finds that funny?
It's pretty funny.
Okay.
It's adorable.
Thank you. Okay. It's just super simple. So P hat, the sample proportion, is given by, you just take this value X, I'll explain what that is, and divide it by N. Excuse me. Where X is the number of individuals in the sample that have a specified characteristic, right? This sample proportion P hat is the statistic that estimates the population proportion P, okay? So P hat estimates P, okay, which is the population proportion. Just a little bit of a sidebar. If anyone ever goes and takes an advanced statistics course, I hope, I don't know, I hope people find these topics interesting. I obviously do. But whenever you see this notation, this caret sign above a value, like if you were ever to see mu with a hat over it, okay, this is just another way of saying the sample mean. All right. Generally, they actually just call it X bar, but so whatever this hat sign over it means is we're estimating the population parameter. Okay, so the population parameter we're interested in is the population proportion, and we just use the sample proportion to estimate it. Okay, but that's just a little bit of a sidebar. So if you ever open up like an advanced stats textbook and see mu with a hat over it. It's just another way of saying the sample mean. All right, everybody okay if I move on?
Yep.
Yep.
All right, let me give you just a quick example here, okay? So in a Quinnipiac University poll conducted in May of 2020, okay, they talked to 1,745 registered voters nationwide, okay? Were asked whether they approved of the way President Trump is handling the economy, okay? So really there's only two things here, okay? Do you approve or not approve? Okay, that's what I mean when I go back here, that there's only two characteristics. Okay, you either approve or not approve, okay? So this right here, this is my N, this is my sample size. Okay, this right here, 349 responded, yes, I approve. Okay, this right here is my X, okay, because I'm interested in estimating the next part here. So obtain a point estimate for the proportion of registered voters who approve, because I'm interested in the proportion to approve of the way Trump is handling the economy. Okay. So this would just be X divided by N. Okay. So I would take what and divide it by what to get this?
You would take 349 and divide it by 1745.
Yep. And you can see here, that's just what I got here. And what we're saying here is the sample proportion. If you take this and divide it by this, you get roughly this. So an interpretation of this would be that 20% of people approve. Just to be clear, I just made these numbers up, by the way. Okay, so don't think that this is really what a poll said. I didn't have time to pull a real one. I'm sorry. So does at least calculating p hat, I mean, super simple, make sense?
Yes.
Okay. All right, so I want to move on. Oh, is everybody okay if I move on?
Yep.
Yep.
All right. So I want to talk now about like an experiment here. Okay. Do you guys remember when I was introducing the distribution of the sample mean? I said things. I was like, "Oh, imagine that the college president called me and she wanted me to get the mean height in 100 classrooms." Does that kind of like ring a bell?
Yes.
And I looked at like the distribution of those X bars. Well, let's just kind of go with this one, okay? It's going to be very similar. So according to a Time magazine poll, right, or Time poll, right, conducted in June 2020, right, 42% of registered voters believed that things will get better in 2021. All right, I'm just curious. Do you guys think things are going to get better in 2021?
I bloody hope so.
No.
I really hope so too. All right. Anyways, let's just assume. Okay, so let's just assume that this is the actual value of the population proportion. All right. So let's just kind of a sidebar here real quick. Like, there's no way that we can actually know what the real value of the population proportion is. Like, there's no way I can call every single person in the United States and say, hey, do you think things are going to get better? But let's just assume that that's the actual real value. Okay. So here's what I want to do. All right. I want to repeat this poll 300 times. Okay. Let me ask you this. Do you think every time I call people and ask them hey, do you think things are going to get better in 2021? Do you think every time it's going to be exactly 42% of people?
No.
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 No, it absolutely will not. Sometimes it'll be 41, sometimes it'll be 45, right? Like it's just going to be all over the place. So I'm going to do this experiment, okay, 3 different ways, okay? So first 300 times. I'm going to call 10 people, okay? I'm going to call 10 people. I'm going to say, do you think things will get better? You're going to get things will get better. And then I'm going to calculate the p-hat for that. And then I'm going to do that 299 more times where each sample size is just 10 people. Then the second time I'm going to do this, the second 300 times, each of my samples is going to be 50 people. Okay, I'm going to 5 times as much. And then the third time, I'm going to do it 300 people or 300 samples. Okay, each of my sample proportions will be 100 people. Okay, so what I'm getting at here is my p-hat here. For the first one is going to be x over 10. The second time it's going to be x over 50. And then the third time it's going to be x over 100. Just as a general concept in this class, okay, do you think samples of larger sample sizes are more accurate or less accurate?
More accurate.
Yeah. So just note. Should be better. Okay, I'm gonna put that in quotation. One other note here. So all these p-hats is a statistic. Okay, like x bar is just a statistic, okay? We know x bar, all right, was normally distributed. So what about p-hat? And you're going to notice something really cool is going to happen, okay? Everybody okay if I move on?
Yes.
Okay. Just stretching first.
I'm doing the same.
Yeah, my son got up like twice last night. Well, my son, just as a sidebar here, what he does these days is like 2 nights in a row, he'll sleep for like 9 hours straight and it's glorious. And then just one night at random, he'll be like, I need to get up like 2 or 3 times. So like, I'm just not used to it. Like it messes with me quite a bit. It does keep me on my toes. It sure does. Okay. So this one here, okay, this is the 300 sample proportions of size 10, okay? What does this kind of look like?
Kind of looks like a normally distributed bell curve.
A normal distribution, sorry, not normally distribution, normal distribution, yeah. Now look, here's the other thing that's really, really important, okay? Remember we said that the real population proportion was 0.42. Look where this looks like it's kind of centered at, okay? Is it not, it's not perfect, but is it close, kind of like to the real population proportion of 0.42?
Yeah.
Yeah, it's close. It's not perfect though, right? Like it's like, it kind of looks like a normal distribution, but not really. Okay. Note the standard deviation too, okay? So it's close to 0.42. The mean of this is real close to 0.42. And the standard deviation, I'll talk about this later on, is 0.160. All right, now I'm gonna redo this experiment again I'm talking about, we're now, instead of talking to 10 people, I'm going to call 50 people each time. And you notice this happens, okay? What does this kind of look like? Looks more like.
Looks more normal.
Yeah, it's getting better. It's not like perfect, but it's definitely looks more normal. Now look at the mean. The mean of this normal distribution, it's really close to 0.42, okay? Now, when I increase the sample size, did you notice how the standard deviation got smaller? You see that? It goes from 0.16 to 0.072.
Yep.
Okay, this is what I mean by larger sample sizes get better, okay? Now let me show you what it looks like when I called 100 people. All right, gosh. Does that look really, really good, like a normal distribution?
Yes.
Yep.
Yes.
Okay. If you look here, now this is where things get a little weird, okay? What we're saying here is it looks like p hat, okay, is normally distributed. Okay, and I want to caveat that with a certain sample size. And I'm going to get to that requirement in a bit. All right. So now here, this is what I mean by it's weird. P hat is a proportion, but when something is normally distributed, okay, we say it has a mean and a standard deviation, okay? So even though we're talking about a proportion, right, we're saying, well, what is the average of those proportions? You know, like, and then what is the standard deviation of all, or so what is a measure of the spread of those proportions? Really, like what's going on here, have you guys ever heard, I don't know how much people watch the news or paid attention to like the political polls for the election, but have you guys ever heard people talk about like, well, the average of the polls, you know, so like, has anyone ever heard that? What is,
Yeah, I just try to ignore them though this year. 2016 was traumatizing.
yeah, I try not to talk too many, I try not to talk any politics, but so like what I'm saying here is like if you know, if one poll comes out to be 0.40, another poll comes out to be 0.44, the average is 0.42. Like we're just taking the average of all the polls. And it looked like the average of this distribution is equal to 0.42. So if you go back, this is really important. That's what we assume the population proportion was. Okay, so the average of the polls, the average of these p hats, it should be the same as the population proportion. Okay, so like if you're thinking about the political polls, what this is saying is like, look, some polls are going to say a certain candidate, this percentage is going to vote for it. Another poll is going to come out and say it's this percentage. But if you take the average of all the polls, okay, the average should be really close to the population proportion. Okay. So the big takeaway here is just like X bar, this statistic p hat, if you have certain requirements, and I'll talk about that, it follows a normal distribution, a normal bell curve, okay? Just as another sidebar, I talked about my wife a little bit in here, right? A little bit, sometimes. So my wife is a pollster. I don't know if I ever told you guys that. And so she says, man, if the polls get it wrong this year, no one's gonna trust her industry anymore. So.
Truth.
Yeah. Is everybody okay if I move on?
Yeah.
Okay. All right, so here's what we notice. Okay, these are the key points from this this example here that I've been doing, okay? As the sample size n increases, the shape of the sampling distribution of the sample proportion becomes approximately normal. So what we're able to say here is p hat is approximately normally distributed. All right. The mean, okay, of the sampling distribution of the proportion, all right, is equal to the population proportion, p. So what we're saying here is the center of this distribution is whatever the original population proportion is. So the mean is equal to whatever the population proportion is, okay? So the kind of the takeaway that I like to say about statistics is on average, you're right. Right. So if you only think about the being on, you're right on average, okay? And the other thing here, talking about the spread, the standard deviation of the sampling distribution of this sample proportion decreases as the sample size n increases. So like if you looked at in all these cases, the standard deviation as we increase the sample size got smaller and smaller and smaller. All right, so now we can finally, oh, sorry. Everybody okay if I move on? I just want to get through the next slide or two, and then we'll take our break and then do spend the second half of class just doing examples. Everybody good? Okay.
Yes.
All right, so now I want to talk about the sampling distribution of p hat, okay? And I'm gonna, hold on for 1 second, I'm gonna go back to like the second example we did. Like here, in this second example, we talked about the sampling distribution of X bar, okay? We said it met certain requirements, it was normally distributed, and the mean and standard deviation. So now we want to do the same thing with p hat, okay? So for a simple random sample of size n with a population proportion p, okay, so this is important. When you do these problems, you're going to be given the value of p. Okay, I'm going to give you the population proportion. All right, the shape of the sampling distribution of p hat is approximately normal provided. So like you know when we did the distribution of the sample mean, we had to do a number check. We had to say, is the sample size greater than or equal to 30? Yes, so this is the number check for this type of distribution. All you're gonna do is you're gonna take the sample size, multiply it by the given population proportion, multiply that by 1 minus the given population proportion. And as long as that number is greater than or equal to 10, all right, you can say it's normally distributed. And don't worry, we're gonna work a bunch of examples with this stuff. All right, the mean of this sampling distribution, so on average you have to be right, so the mean is going to be equal to, we're going to denote it as mu sub p hat instead of mu sub x bar, and that's going to be equal to whatever the population proportion is. And the standard deviation of the sampling distribution of p hat, this is also referred to as the standard error. Okay, we denote it instead of sigma x bar, it's sigma p hat. And it's just this really simple formula we'll do in our calculator, okay? It's just the square root of p times 1 minus p divided by n. And when you do this in your calculator, okay, this is important note. Always go to at least 4 decimal places here. Okay, always, always, always. You guys okay if I move on?
Yes,
Yes.
Professor.
Okay. All right, so the model on the previous slides requires that the sampled values are independent, okay? So this won't ever be the case, okay? But when you sample from a small population, all right, you just have to verify that the sample size is no more than 5% of the population size. And I'll even show you that check when we do our first example to show you that, you know, hey, you know, is our sample size less than 5% of the population size? And then regardless of whether this value checks out or not, the mean of the sampling distribution is still P and the standard deviation is still this. It just won't be normally distributed, okay? But the big important things, like we're gonna take our break now, but the big important things are these three values here. Does this number check out? What is the mean? What is the standard deviation? Okay. What do you guys think? Is everybody, what we'll do now is we'll take a 9-minute break or so, and then we'll come back and we'll do, all I've got is 2 examples for the rest of class for us.
Good.
Sound okay?
Yeah.
Yes.
All right, let's be back at 10 a.m. I'm gonna go grab some coffee. I encourage you guys to as well. All right, I'll be back in 10 minutes. All right, yep, just checking my mic again. Everybody can hear me okay?
Yes, sir.
Yeah, we can hear you.
All right. So let's finish up for the morning. All I want to do now is just 2 examples of how we're going to use this, and then these examples are really going to follow exactly like what you'll see on your quiz this week. Okay, so if you pay attention to these 2, honestly, if you pay attention to the next 2 examples, you'll be more than ready for your quiz this week. Okay. So here's the first example, right? So as of 2007, so this is a while ago, okay? The United States Census Bureau reports that 27%, so for these next 2 examples, by the way, I didn't make these numbers up, okay? So these are real numbers. Reports that 27% of the population has attained a bachelor's degree or higher, okay? So suppose a random sample of 200 adults is obtained, okay? So here's what we're gonna do, just so you get the idea. We're gonna sample 200 adults. And we're gonna record the proportion who have a bachelor's degree or higher. Okay? Sorry about the phone in the background. All right, so here's the whole concept of this. Do you guys think every time I call 200 adults, I'm gonna get the same proportion every time? Or do you think
No.
it's gonna, yeah, sometimes, I'll get different, it just depends on who I randomly sample. Okay. So the next question says, so the next part here says, describe the sampling distribution of p hat, okay, the sample proportion of adults who have a college degree. So I'm gonna define my variable p hat, okay? P hat is gonna be equal to the proportion of adults in a sample of 200 who have, it should be bachelor's or higher. So basically what you want to do is you want to verify that this p hat's going to be normally distributed. So I'm going to go back a slide for a second. Okay. You're going to have to check this number check right here. Okay. This n times p times 1 minus p has to be greater than or equal to 10. So n times p times 1 minus p has to be greater than or equal to 10. All right, so my n, this is my n. It's the people that I sampled. So it's 200. This is my p. This is my population proportion. So like what we're saying here is, we're going to believe the Census Bureau, all right? And we're going to assume that the real population proportion is 27%. And then I have to multiply that by 1 minus 0.27. So let me grab my trusty calculator here. So I'm going to take 200 times 0.27 times, then in parentheses, 1 minus 0.27. I'm just curious, did anybody follow along, get that number with me?
Yes.
So we got 39.42. All right, is that greater than or equal to 10?
Yes.
All right, so this checks out. So Also, going back just real quick, I'll never do this check again, but like, so we're talking to adults in the United States, okay? So what we have to say is that our sample size is no more than 5% of the population size. So is 200 adults less than 5% of all the adults in the United States?
Probably, yeah.
I mean, yeah, I mean, there's probably, you know, 150 million adults in the United States. Maybe more, maybe 180, I don't know. So yeah, it's way less. So that'll always check out. So as long as this checks out, thus, the sampling distribution, so we're describing the sampling distribution, of p hat is normal with, so when something is normally distributed, you got to give the mean, which we denote as mu sub p hat. So looking back, mu sub p hat is equal to whatever the population proportion is. Okay, so what is the population proportion here?
0.27.
Yep. So look, this is all this is saying is, hey, look, when we call 200 people, sometimes we're going to get values greater, proportions greater than 0.27, sometimes less than 0.27. But on average, the average of all these proportions should be equal to whatever the real population proportion is. And then you also need to say the standard deviation. In this case, we call it the standard error. And basically it's like, hey, look, I know I'm not always going to get 0.27. So what is the average error I'm going to make? And you just have to follow this formula. It's P times 1 minus P, all over N. So it's just this formula right here. So it's the square root of 0.27 times 1 minus 0.27 divided by the 200 people we call. So you just have to be careful plugging this into your calculator, right? So I'm going to do it on the TI-83. It's a little bit easier on the TI-84. But I'm going to go second function, parentheses. So 0.27 times, then in parentheses, 1 minus 0.27. Close that parentheses. Divide by 200. And then close the outer parentheses. How many people got that value right there, just out of curiosity?
Yep.
Yes.
Okay, and how many decimal places did I say to go out in this one?
4.
Yeah, this is incredibly important. Whenever you do this problem here, you have to go out at least 4 decimal places. So 0.0314 when I round it. Okay. So here's basically what's going to happen. I told you it's normally distributed, mean, standard deviation. Now I'm just going to ask you some probability questions. Okay. Is everybody okay if I move on?
So when you're asking for us to describe the sampling distribution, you just want the new standard error and the new mean and the number check.
That is correct. Yep. The good news is on your quiz this week, I'm not going to ask you explicitly to describe it, but you're going to need to find these on your own. Okay, so basically the question on the quiz is going to immediately jump to this stuff right here, but you're going to need to know the mean and standard deviation, standard error to answer them. Okay.
Yep.
All right. Everybody okay? Can we move on? All right. So keep this written down because we're going to need it for the next one, all right? So now the problem says, in a random sample of 200 adults, what is the probability that less than 25% have a college degree? So basically what I'm asking you is this, okay? What's the probability that your sample proportion p hat is less than 0.25. All right, so how are we going to answer this? All right. Well, it's just a normal curve question. All right. So I'm going to sketch the distribution of p hat. So it's normally distributed. The mean should be 0.27. And I want to be less than 0.25. And am I going to shade to the left or to the right?
Left.
Yes. So guess what I'm going to use now in my calculator to solve this?
Normal CDF.
Normal
Normal
CDF.
CDF.
So again, it's still the lower, the upper, the mean, and the standard deviation. Always, always, always. So treat this just like before. This is a probability to the left. Okay, so what is my lower going to be?
Negative 9999.
Mm-hmm. My upper, I'm going to stop here. Now the mean is mu sub p hat, and my standard deviation is sigma p hat. That's why we found them in the previous slide. Okay, so the average is 0.27. And the standard deviation is this number right here, 0.0314. So second function distribution, normal CDF, negative 9999, comma, I want to go up to 25%, so 0.25. On average, I should be 0.27. And we found that standard deviation How many people got this? If you did follow along with your calculator.
Yes.
Yep.
Yep. Yeah. So it's, oh, I forgot it. 0.2621. Not too bad.
No?
How do you know when to use the bigger sigma calculation versus the sigma
That.
over the square root of n?
Totally. Yep. So whenever there's a problem that talks about a sample mean, okay? So let me go back. Sorry, this is going quick. Mean. Whenever you see the word mean, sample mean, you're going to use the over the square root of n, okay? Whenever I give things like an average and I tell you the standard deviation right there, boom, you're going to use this formula. You use this new formula stuff whenever you see percentages, okay? Like, let me show you on your quiz real quick, okay? This is your quiz, right? So like questions, question 3, mean charge life. Do you see that right there? And then when you get to question 4, notice how all of a sudden it's talking about percentages?
Yes.
That's how you know.
Okay. Thanks.
Yep. Yep. That's how you know. All right, let's do the next one here. In a random sample of 200 adults, what's the probability that more than 30% have a college degree? So now it's the probability that p hat is greater than 30%. So I'm just going to sketch it again, right? P hat is normally distributed. On average, should be 0.27. I want to be greater than 30. So I'm going to shade to the right now. Whoosh, just like that. So what am I going to use in my calculator?
Normal CDF.
Normal CDF. My lower here is now 0.30. My upper, because it's to the right, is going to be 9999. The mean doesn't change, it's 0.27. And the standard error, standard deviation doesn't change. So I'll do this on the TI-84 now, so you can just see. So second function distribution, normal CDF. The lower, in this case, is going to be 0.30. The upper is 99999. The mean is 0.27. And the standard deviation is this 0.0314. So it should look like this in your calculator. When you hit enter, and do you get this? 0.1697 when I round it?
Yep.
And that's it. Think you guys can handle this? Does it seem
Yes.
Generally, you know what I find? I find for as long as I've been teaching this, like these formulas aren't like really that crazy. You know, the calculator's really easy. It's just like understanding what exactly the problem is asking you to do. Right? Like if you know the steps you have to take, then boom, 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 this is easy. It's just like your question. Excuse me, how do I know it's a mean versus, you know, which formula to use? Like once you can figure that out, then the problem just falls right into place. All right, you guys ready to see one more?
Yes.
Yes.
Yep.
Okay. So this is our last example for today. According to the most recent General Social Survey, which is a real survey, by the way, 21% of adults have at least one tattoo. I'm just curious, what do you guys think of that, that percentage? Do you think it's high? Do you think it's low?
I think it's a little low, to be honest.
A little low? Anybody else?
I was gonna say a little low too, only because like
Yeah.
older generations have army tattoos and stuff like that.
So it's really interesting, right? Like, so I'm pushing 40, so I'm a different generation than many of you. When I saw this number, I was like, oh my God, that's so high. I was like, really? And then what's really interesting is this is 21% of all adults, regardless of age. But when you break it out by age group, so like if you look at people who are like 18 to 29, it's almost 40%, which is like, so it's just really interesting, like the generational differences, you know? So anyways, I always like to do this example because I find it interesting.
They're easier to remove now. I think it's probably like less permanent than it was 30
Maybe.
years ago. So
Sure.
people are more willing to get them.
Yeah. I thought I'd get one, like a big angel covering my entire back.
Yeah.
That's a joke. I'm wouldn't.
I have a few that I like went in knowing I could always get removed. So
Professor, my husband has one tattoo, just one tattoo, and it's like a tiny elephant in his ankle. So he's like, I don't ever see it.
That's charming, you know.
Yeah, he got it in Thailand. He was drunk, and you know, it's just a crazy story.
You know, maybe we should tell that story when the recording's off. Anyways, according to the most recent, okay, so 21% of adults have at least one tattoo. So here's what we're gonna do. This right here, this 21%, okay, this is my P, okay? Did you notice how, like in the previous example, I wrote it explicitly for you here? Here, it's not going to be explicit, like on your quiz and stuff. And then suppose a random sample of 400 adults is taken and the proportion of at least one tattoo is recorded. So here's N. This is my sample size. Okay. So the first question here, all right, let's describe the sampling distribution of p hat, the sample proportion of adults who have at least one tattoo. So I'm going to start again by saying I'm going to let the variable p hat be equal to the proportion of adults in a sample of 400 who have at least one tattoo. All right, so you got to do the number check. So the number check is just n times p times 1 minus p, and just has to be greater than or equal to 10. And I'll give you guys a hint, okay? Every single problem I ever ask you in this class, and like even on your final and stuff, the number check will always check out, okay? But let's just go through it. So we're going to take the 400 people. P was 0.21, and I want to do 1 minus 0.21. So I'll do it on the TI-84 this time. So second function, square root. I'm going to do 400. Oh, why am I doing square root? My gosh. 400 times 0.21 times 1 minus 0.21. Did anybody following along get this number?
Yes.
Okay, so it checks out.
Yes.
So 66.36. Okay, so we can now say thus the sampling distribution of p hat is normal, is normally distributed with mean mu sub p hat is equal to p. So that's this 0.21. And standard deviation, you just got to go through this formula, this p times 1 minus p over n. So it's the square root of 0.21 times 1 minus 0.21 divided by our sample size of 400. So I'm going to do it on this calculator here. So square root 0.21 times, and then in parentheses, 1 minus 0.21, close the parentheses, divide by 400. Do you get 0.0204 when you round it?
Yes.
0.0204. All right, so this right here is the most important stuff, okay, for the problems. All right, this is because we use these values in our calculator. All right. Do you guys kind of see now how this is all just going to fall into place, and then you can just like hop right to your calculator and it's not too bad?
Yeah.
Yes. So like in an answer, like say on the final, it says describe the sampling distribution. You want mu sub p hat, sigma p hat, and then you want us to say that p hat is normally distributed.
So what I would need to see is this number check right here. Like I need to see the number check. right here. And then as long as it checks out, which it will, then you just need to say the sampling distribution of p hat is normally distributed with, and then you just need to give me the mean and standard deviation. Okay?
Got it.
Gosh, this is a terrible circle here now, but you get it. Okay. All right, in a random sample of 400 adults, now what is the probability that less than 20% have a tattoo? So it's the probability that my sample proportion is less than 20%. Well, I mean, you can obviously see how you can do this. It's normally distributed, so the bell curve. It should be centered at 0.21. And I want to be less than 0.20. So it's a tail area to the right, or to the left. Holy cow, tail area to the left. Haven't had enough coffee yet. So it's a normal CDF. What's my lower value I'm going to plug in?
-9999.
Yep. I'm going to go up to 0.20. The mean 0.21, and the standard deviation is 0.0204. I'll grab the TI-83 here. So second function distribution, normal CDF, -9999, comma 0.20, comma 0.21, comma 0.0204. How many people got that?
Yep.
Yep.
Yep. So it's 0.3120 when I round it. Also, by the way, don't stress if you round incorrectly on the quiz. So I have a tolerance built in. So like if you would like on the quiz put 0.3199 like or 19, it's okay. All right, so don't stress too much with the rounding. All right, you ready for the last problem?
Yes.
Yes.
All right, a little bit of a stretch. Now this is weird. In a random sample of 400 adults, what is the probability that more than 96 have at least one tattoo? This is weird, right? Like every single problem I've done, it says, oh, less than 20%, more than 30, less than 25. But now all of a sudden there's no percentage here. So I just want to be more than 96 in 400? Do anyone have a suggestion how I can answer this?
Can you just calculate like what percentage 96 is about out of 400?
Yep, exactly. So this is a little bit of a trick question. So just whenever you see that, you just need the extra step. You just need to convert this to a p hat. So p hat is x over n. So it would be 96 over 400. So it's 0.24. So now what I'm asking you is I want to find the probability that my p hat is greater than 0.24. Okay, that's it. So whenever you see these numbers, it's like, oh, they're talking about percentages, but then it gives a more than a specific number. You just need to take that extra step and change it to a proportion. So bell curve should be centered at 0.21. And I want to be greater than 0.24. So this is the last time I'm going to ask this, but what option in my calculator am I going to use?
Normal CDF.
So my lower is 0.24. My upper, because it's a tail to the right, is 99999. The mean is 0.21. And you just have to go back. The standard deviation was 0.0204. Second function distribution, normal CDF, 0.24, 9999, 0.21, 0.0204. Do you get this when you do it?
Yeah.
Yeah.
0.0707. And that's your answer. What do you think? Not too bad? You guys think you can handle
Not too
this?
bad.
I'm sorry?
Not too bad.
All right. Let me stop the recording now, and then I just want to say a few things.